All right, welcome. So in this video, I want to continue talking about asymptotic bounds and asymptotic notation. And I want to introduce a new tool to our kit called the limit test, which will help us prove some asymptotic bounds and using our asymptotic notation. Specifically, it will help us prove some big theta bounds. And it will also help us prove two new types of asymptotic bounds called little o and little omega, and maybe I'll start by introducing those two. So little o and little omega actually fill in two of the gaps that I guess are missing in our intuition. So let's sort of follow our intuition where it is, identify the gaps, and sort of see why little o and little omega fill them in. So first of all, we introduce big O as a relationship between two functions. That sort of means one is less than the other. Less than or equal to, we were saying. Okay, f of n is less than or equal to g of n. Big omega, then, is the opposite case. It's the greater than or equal to. So we sort of just flip the sign around to get there. And we saw when you put those two together, if the relationship goes both ways, f of n is less than or equal to g of n, and f of n is greater than or equal to g of n, then at least the way it worked with numbers, and so also the way it's going to work with our intuition and our asymptotic notation, so that usually would mean that f of n is equal to g of n. That makes sense then. If one is less than or equal to and it's greater than or equal to, then it must be equal to. And so we called that one big theta. So I said we've kind of got some missing gaps here. Well, those missing gaps are for the strictly less than and the strictly greater than. And that's where the little o and the little omega come from. Okay, so little o is related to big O in that it is big O is less than or equal to, but little o is strictly less than. So when these functions, what that means is the function g of n grows, we sometimes say grows strictly faster than f of n. So the growth rate is faster. And then the opposite is true, of course, for little omega. It's got the same relationship to big omega. Again, if you're not familiar with your Greek letters here, this is the capital letter omega. This is the lowercase letter omega. At least when I draw it, I usually put a little tick on that, but at least in this font it doesn't have it. And then that's the capital theta, and you may have encountered a lowercase theta before as well. In any case, we don't use the lowercase theta, we only use the lowercase omega and the lowercase o to represent little o and little omega. Now, here I've got some formal definitions as well, although we will typically, when we're trying to prove these relationships, rely on the limit test, usually just because it's a straightforward and easy to apply test. But let's just look here at the definition. Now what we'll notice here is there's only been one thing that's really changed. I guess so, maybe two. We've changed here this symbol, as we might have implied from our intuition down below. We've changed the less than equals to a strictly less than. Okay, and that's one of the things we've changed here. Now the other thing we've changed is the logical quantifier that we applied to our constant b. Before it was there exists a positive constant b, and now it says for every positive constant b. Okay, that changes the whole meaning of the sentence. Okay, and this is why we often want to codify these sentences in logic, so we can get them right down into their symbols and see, oh, this one means something different. This means something different. So let's see if we can see what it means. This one's saying for every constant b we can put here, big or small, but has to be positive, not 0 or negative. There is some positive constant. Now there exists, we're back to the exist part here, there exists some positive constant and not such that, and now the for all again, the rest of this sort of reads similar as before, such that for all of the n's past and not all of them after this cutoff point, it is the case that f of n is less than b of n. Okay. Now what that means for us is no matter what we inflate, no matter what constant we put b out there, there's going to be some cutoff point, there's going to be some crossover point is another way to think of it, where these two functions cross over and b times g of n is still greater. Okay. Now, maybe let's take this a moment to try and understand maybe visually what this means. So I'm going to put one function in here that I think might be just easy for us to understand. I'm just going to do straight n. Okay, this is just n. It's a linear function, and hopefully most of us sort of understand how that works. Now, we could draw a couple other functions here. Actually, I'm going to draw one. I'm going to try and do a good job of it, and it's a little bit tricky, of course. So I can put this function here, n squared, okay? And what we might notice, if we know, of course, here, that 0 squared is 0, right? So that's why they line up here. We'll notice, and maybe I'll put here, that at 0.5 squared is actually a quarter, right? 1/2 squared is 1/4. That's why I drew it underneath the line here, right? And of course, if you're familiar with this, you know that between 0 and 1, the n squared is actually less than. That makes it smaller. Squaring it makes it smaller. But once we get to 1, and I guess I drew my crossover point here a little off, but once we get to 1, we're back to the case where 1 squared is equal to 1. But then, of course, as we probably are more understanding here, that after this point here, okay, after this point here, we know that n is less than n squared. Okay, but what's the number hiding out front here? I kind of left space for it here. At the moment, it's 1, right? And we're saying that this is true, that if the number we put out front here, and we were calling this b in our definition, this number, maybe I'll put it here, b. If b is 1, then we can see here that for all n greater than or equal to 1, our relationship holds. Okay, but what our definition said is it said for any b. For any b, we should be able to find this crossover point. So what b could we pick? Okay, now here I'm going to do something that is our intuition. Normally we want to make b bigger, but in a second I'm going to make it smaller because that's actually the trickier dimension. If we change b to 2, we're now talking about 2n squared. And what happens with 2n squared? Well, we'll just double all these, and now I'm going to have a tricky one to draw. Oops. Okay, not very good, but the idea here was, oops, my crossover point should be at about the half point now. Now that 1/4, right? You know, if we plug in here n equals 0.5, we get n squared equals 0.25, multiplied by 2 again gives us right back to 0.5. We found the crossover point again, okay? Now in this case, the crossover point is getting closer to 0. If I pick b equals 10, you know, it's down here somewhere, okay? But what happens if we try and make b smaller? Let's say b is half. Okay, now where is the crossover point? So again, let's look at our math. We're saying n is less than 1/2 of n squared. Is this true? Is this true in your mind? Well, let's be careful here. At some point here, at this point now, if we do our 1/2, that's, you know, okay, I'm going to keep drawing it. This is maybe our 1/2 n squared. Now the way I've drawn it, there is a crossover point here, so that's good. But the question is, where is that crossover point now? Because here, when we're at 1, it should be at 0.5. We haven't crossed over yet. We still need to come our way up. to here. Now I don't know if I've drawn the crossover point in the right location, in terms of scale that is, but maybe I have. Let's see if we can figure it out. Okay. So the crossover point, of course, I think as I'm trying to indicate here, depends on our b, so we need to work with this mathematical equation here, or inequality here. This is not equation. Equation is when we have an equals. This is an inequality. So where can we go next with this? Well, what I might do here is I might do something like this, right? Let's see what happens if I can do something like this, okay? Now I've just crossed them off. What I did here is I canceled out one n on each side, dividing by n on each side, giving me just n over n is 1 on this side. 1 must be less than or equal to 1/2 of n. Okay, looks like we can take this to where we need to go. We just need to go a little bit further. It looks like if we go one more step, I can just multiply both my sides by 2. And it looks like this works when n is greater than 2. So now it looks like we found a crossover point here of 2. Now let's see, does that make sense? Now hopefully some of us might have already plugged that into our internal math calculator and figured this out. But if we take 2, if n is 2, so this is n equals 2, if we take our formula here, 1/2 of n squared, well, n squared is 4, of course, and then divided by 2 again gives us back to 2. That's what we're looking at, the crossover point. Okay, maybe let's do just one more time. This was b equals 1/2. I'm thinking, well, maybe someone says, look, is this always going to be true? If we went to, I'm going to pick this one here, b equals 1/10 or 0.1. Okay, that means, again, going back to our math here, we've kind of changed this to a 10 now. 1/10. That means we've made this line even smaller. Okay, I'm definitely not to scale now, because if your internal brain calculator's following along here, you can probably tell me which value of n our crossover is going to be now. Okay, when is n going to be 1/10? So maybe I'll just do on my scratch here. N needs to be less than 1/10 of n squared. Let's cancel our n out again here. It looks like we've got 10 must be less than n. So maybe our crossover point now is 10. Okay, I think we've done enough exploring of that sort of idea that we can see what the definition is trying to tell us. It's saying that, again, for any choice of our b here, no matter how small we can get it, but not 0, it has to be positive, we will result in a case where there's some crossover point where f then is always less than b times g of n after that point. So we did that with two example functions, n and n squared, and I chose n and n squared because n, our f of n, is indeed in little o of n squared. That relationship will be easy to see. And we did it sort of visually there, but we didn't actually prove it using our definition. Now, big omega, of course, is just the other side of the coin, flipping it around. So we also have the for all out front here for our a, but now we just switch to greater than instead of less than. So again, this is sort of a little cheat sheet here in terms of your intuition. Maybe it's been a couple weeks since you reviewed this material and you think, well, what did big omega mean again? You can go and use that sort of intuition. Now, of course, this isn't just intuition. I've plucked out part of the definition, but I've sort of forgotten the constants and the extra logical machinery that makes that the definition work. Okay, so let's take these new definitions, which fill in our gaps, as I mentioned, and you see how we can use our new tool, which we call the limit test, to help us determine what the relationship between two functions are. So let's just look at this limit test here. It's a theorem. And I'm not actually going to prove the theorem, primarily because that's going to rely on a little bit of calculus, and I don't want to go into a lot of calculus here. I'd rather just let us rely on some of the calculus knowledge that we've probably built up somewhere else. So if you're unfamiliar with how limits work or some simple calculus, I encourage you to pause this and go review your calculus, and then come back when you are comfortable computing some limits. Okay, so let's look here at this definition. It says, say we've got two functions, f of n and g of n. Now, in this definition I said, let them be two runtime functions. And that means let them be well behaved in the way that I've mentioned in previous videos. That is, they're probably going to be positive and increasing, or at least not negative and not decreasing, and at the very least, not negative and not decreasing as we approach infinity after some cutoff point. So that's what I mean by runtime functions. Here is well behaved so that we don't have to worry about some weird functions. There are some weird functions that don't behave well when it comes to these asymptotic growth measurements, and so there's no point in worrying about them. If you're a mathematician, you might want to go out and say, hey, well, what happens when I put sine in or tangent into one of these? What's going to happen then? And the answer is going to be weird for a bit, but you could still probably get an answer. You could probably still say sine of n is in big O of something, or big omega of something, and so on. But some of them you might fail to be able to compute a big theta class for them. Some of them won't actually have a useful theta class. And so therefore there might be, there might be some confusing math or tricky math that shows up if you go outside the realm of runtime functions. And again, for my purposes and for this series of videos, I'm going to assume that we're working with well-behaved runtime functions, and that's because we're going to assume that the subject matter that we're talking about is algorithm and algorithm analysis. Okay, so let's look here. We've got these two runtime functions, f of n and g of n, and actually what we're going to compute is first the ratio, and then we'll take the limit of that ratio as it goes to infinity. We'll take f of n over g of n. You can put g of n over f of n because there's nothing here that privileges one over the other. But usually the way we do it is we put it in the order that makes it easier to compute. And so that means if you've got, something like n squared plus 4n plus 3, and you've got n squared, well, you put the n squared on the bottom. It's easier to divide out by n squared than it is to divide out by n squared plus 4n plus 3. Okay. So that's just sort of and of course we have the freedom to put them in whichever order we want. Okay, but putting them in a particular order means we need to keep in mind what order we put them in, because depending on what output we get as the limit, if the limit is a constant, then it didn't matter which way we put them, it will still be a constant the other way, just the inverse, right? But if it is 0 or infinity, we get the other one when we invert it, so we want to make sure, because otherwise we'll draw the wrong conclusion. Okay, so let's look at what we do when we compute this limit. We're going to take the limit, we're going to take f of n over g of n as we go to infinity, and if you want, pick a couple functions that you like n squared over n, or n over n squared, or even n over n. Each one will give us a different case. Let's start with n squared over n. F of n is n squared, g of n is n. That's a simple enough limit that hopefully we can see, okay, quickly cancel out an n, and we can see that's just the limit as n goes to infinity of n. Well, that's infinity. Okay, so if that's the case, and in our example case we had n squared in n, and we know the relationship between those two, n squared grows faster than n, or the way we want to write that using our asymptotic notation is f of n, or n squared, is in little omega of n, or g of n. Little omega, remember, being strictly greater than, the greater than sign. Okay, that's when we had n squared on the top and n on the bottom. What if we flip them around? If we had n on the top and n squared on the bottom, again canceling them out, we're now taking the limit of 1 over n. Well, that we know, of course, goes to 0. And that was when we flipped the relationship around. Instead of the greater than we had here, we now flipped it around, so that gives us a less than relationship. If our limit goes to 0, then the one on the top must grow slower than the one on the bottom. Just like we saw above here, if it goes to infinity, then the one on the top must grow faster than the one on the bottom. Okay, so we've got we've got the greater than and the less than relationship. So what happens in the in between? Either we go to 0, shrink all the way down to 0, or we go all the way to infinity, or we end up with like some constant in between, like 1 or 2 or 1/2 or a million. There's a lot of constants in between, of course. Any non-zero constant is fine. If you get a non-zero constant, then that means they grow at the same rate. And here I need to be very careful. When I say at the same rate, there's a big asterisk on the end there. When I say rate, I mean asymptotically, which means up to a constant amount of difference. So let's just take a quick look here. Imagine on the top, I have 2n, and on the bottom, I have n. Then my limit will be 2, a non-zero constant. This will mean that we are in theta of one another, and that maybe makes sense. Hopefully we all understand that 2n is in big theta of n. Okay. But we want to say that these two functions grow at the same rate. They don't grow at exactly the same rate. In fact, 2n grows twice as fast as n. That's what this limit of 2 means when we get here. It means it grows twice as fast. But the way that asymptotic notation works is that twice as fast, as long as it's only a constant scalar multiple, then we count that as the same rate. N we count as the same rate as 2n, 2n is the same rate as 10n, 10n is the same rate as a million n, or 1 over a million n. Those all asymptotically, in big O notation, all are the same. And so, what makes them different? Only if you multiply them by something that is not a scalar, a constant. Something that is a variable, another n. Or maybe a new variable, like n. Okay, so n is not in big theta of n squared, because that's n times n. Okay, and we can push this and test this a little bit more as we look at some more examples. Okay, so what the limit test does for us, what the theorem is allowing us to do here, is says compute this limit, which depending on the functions you have, a lot of them, that can be very easy, or so easy like we did with a few quick examples here, you can just do in your mind. Then if you know what the outcome is, you're done. You just already know what the relationship between those two functions are. And while there's sort of 3 outcomes here, most of the time you're just trying to eyeball because you want to prove something's in theta. That's what you're hoping for. But every so often you want to show that 2 functions are not growing at the same rate, and then this test shows up as well as a good test to do that. Okay, let's take a look at an application of the limit test here. Here I've just picked a couple functions, 4n squared minus n, and I want to show that this is in little omega of n. So this is similar to what we just did in our quick little example. We just picked n squared and n. But this one I made a little bit further, so maybe the limit itself isn't immediately straightforward. Some of us might be comfortable enough with limits to know what the limit will be. But I want to, well, let's calculate it. Okay, so the way we're going to set up the limit again is we're going to take our 2 functions, f of n and g of n. F of n is 4n squared minus n, and g of n is n, and we're going to compute the ratio. So again, like I mentioned on the previous slide, I'm going to take the simpler of the functions and put it on the bottom, just because it's easier to divide out by n than it is to divide out by 4n squared minus n. Okay. Now, the way I'm going to do that, so here I've got it written all as one limit, but here I'm going to want to compute my limit simplify my limit before I compute it. So the first way I'm going to simplify it is by splitting my 2 terms up and distributing the denominator amongst them, because we can see that that's going to make it pretty easy to cancel out some n's. So I'm going to cancel out. This one's going to end up being just the limit of 1. So I'm going to write that as the limit of n to infinity of 1. I've taken the minus and put it out front. We could have written plus minus 1. That would be the same. And then this function here, I've just canceled out the n here again, leaving us with 4n, and this is the limit as n goes to infinity. Now, we can of course see here, what are we going to get? Well, this one's going to be infinity. Infinity minus 1, of course, is still infinity. And so that's it. We're actually done. All we have to do is go back to our little cheat sheet, or if we remember what the limit test tells us, if we get to infinity, that means the one on the top was faster than the one on the bottom, or the omega relationship that we were looking for. So we can immediately conclude, once we've calculated the limit, what the relationship is. So we're done. So this is an alternative to using, of course, the definition. So let's try it one more time. That was an occasion where we would prove a non-equality, a little omega relationship. And now I want to show how we more often use it, which is with a big theta relationship. To do a quick big theta. Now, we've looked at this in the last video. We could use the definition of big O and big omega to find an upper bound and a lower bound on this polynomial of degree 3, this cubic. Okay, now I'll leave that as an exercise if you want to practice. It's not very tricky using the tools that we used last day. But I want to use this opportunity to practice our limit test. So to do that, I'm going to once again use the limit test on this one by computing the limit of these two functions, specifically this degree 3 polynomial over n cubed. Okay, so we'll do that here again, computing again that ratio. And as we did last time, first step, just distribute that n cubed out a bit so that we can do some simple division. Now, in the last case, we got a lot of canceling out, and it made it a little bit easier. In this case, well, there's nothing to cancel out here, but there is something to cancel out here. So let's see how these work. Okay, we'll do some canceling, all of our n's, and we're left with still 3 terms. So the first one, the n cubed, all canceled, we just get 6. And then hopefully what our own familiarity with limits can tell us is that these ones here, well, we've still got some variable on the bottom, but we've got a constant on the top. So this is going to shrink. These ones are going to shrink away as our n gets really, really large. So what we can do is, once we split the limit out amongst all 3 components here, we end up seeing that, yes, this limit will be 0, and this limit will be 0. And so we end up with 6. And so our conclusion, again, going to look up the limit test, or if we're familiar with the limit test, we know that the conclusion we should draw is that this is going to be big theta, a theta relationship when we get a non-zero constant. If it's 0, we get the little o, but if it's a non-zero, like 6, then it's theta. So we're done. Again, we just say, we already know how the limit test works. It's a tool, so once we're done with it, we just say by the limit test, this is the bound. Okay, so a couple quick examples of the limit test. Let's see how else we can use the limit test. This is to help us prove a couple of quick rules of thumb that are helpful. Build your intuition up when you're talking about big O notation. Okay. One of those rules of thumb, as I already mentioned, are things like lower order terms don't matter. And then we just saw earlier that a multiplicative constant out front, like a 2n, doesn't matter either. Okay. Well, here what we're going to do is we're going to show that some things do matter. So one thing I want, or at least what it says here, is logarithms are dominated by polynomials. That's what we're saying there, is that all logarithms, no matter what kind of logarithm you have, are always going to grow slower than a polynomial. What kind of polynomial? Any kind of polynomial. Now, I could actually prove a stronger theorem than this, but to do that would involve diving a little bit deeper into the limit test than I want to. We can, of course, do it, but I want one that's somewhat straightforward for us to calculate the limit together. And so what I've done is I've picked 2 functions. I've chosen log n, which is a good representative function, but there are other functions that we might be curious about. Log of a different base. We could take log n and multiply it by itself to give us log squared n. So you could get polynomials of logs which might be interesting too. But I'm just going to restrict ourselves, like I said, to a simple version of the log function, which is just log base 2 of n, which is one that we as computer scientists encounter the most. And then what I've chosen here is a polynomial of degree d, but I've just said for d greater than 0. Now I might have chosen here, and in fact a good choice here might have been, instead of d, the symbol epsilon. Now why would I choose epsilon? So some of you may know from maybe work in calculus or other math that the lowercase Greek letter epsilon is often used for positive constants that are intended to be very small, okay? So why would I use epsilon here is because actually I want us to think about the case here where d is very small. So what kind of small d's are we talking about here? Well, d equals 1 is a linear function. That is something where d is small and still greater than 0. But that is still a kind of big D from the perspective that I'm taking here. Now I'm thinking, well, we probably know, or we have some experience to know that, well, log n grows slower than n to the power 1. Hopefully we have some intuition there. If not, this limit test is going to fill it in, okay? Log n is slower than n, okay? But what about n to a power less than 1, like 1/2, the square root of n? Is log n still slower than square root of n? The answer is yes. Is it still slower than the cube root, the fourth root, the 100th root of n? The answer is still yes if this theorem is true. Because what this theorem is saying is pick any root, any small fractional exponent that you're interested in, as small as you can get it, 1 over a million, 1 over a billion, and logarithms still grow slower. And remember what this still grows slower means is there is a crossover point somewhere that we can find where this n to the 1 over a million will cross over and grow faster than log n. Even, surprisingly, if we put a big number up front, like a billion log n. Okay, so that's what we're trying to prove. How can we do this? Well, the little o is showing up. Maybe we can use a limit test. Let's throw it in a limit test. Okay, so I'm going to start my limit test off, and I'm going to pick some d greater than 0, whichever one you like. Okay, and I'm going to pick this. I could have done it the other way. I could do it this way. Okay, whichever way I want to do it. If there's not going to be an easy cancel, I sometimes just put the little one on the top and the big one on the bottom. If I expect or I already know which one I think is little and which one is big. If I don't, then I'm just guessing, so who cares? Just put one on the top and one on the bottom and see what you get. Okay? So in this case I put log n, and here we're actually stuck. If you go back to your calculus text or you think about your limits, think, well, I've got an infinity on the top, I've got infinity on the bottom, so that's infinity divided by infinity. And we crack open our old dusty old text and it says, oh, when you're in this situation, you use L'Hopital's rule. What does L'Hopital's rule say? L'Hopital's rule says that if you're taking the limit in this way, and you end up getting an infinity over an infinity, or some other combinations like an infinity minus infinity or infinity times infinity, weird things like this, that in these scenarios, you can still compute the limit if you compute the limit of the derivative of the top divided by the derivative of the bottom. So we're going to just take the derivative of both of our functions, again, busting out some calculus. And then if that limit still exists, so sometimes you do that and things get weird and get messed up. You might end up dividing by 0 or something weird like that. Well, if something weird like that happens and the limit doesn't exist, well, too bad. You don't have any, L'Hopital's rule doesn't work, okay? But if the limit does exist, what L'Hopital's rule says is the limit will be the same after you take the derivative. So that's what we're doing here. We're going to take the derivative and see if it helps us. Okay, so let's see what happens when we take the derivative. First of all, let's take the derivative of this guy, log n. Now, we might be thinking, well, that log base 2, maybe I should have picked log base e, because taking the derivative is a little easier than natural logarithm. But no, that's fine. And in fact, I'm going to be very honest here. As a computer scientist, I actually studied my calculus a couple decades ago. Just for the record, calculus hasn't changed. But I haven't actually needed to practice a lot of it, other than when I'm teaching, in a long time. And so for me, in my computer science brain, the fact that the constant here is 1 over the natural logarithm of 2 is something that I've actually forgotten. Luckily, my slide has this number on here to remind me. And in my brain, what I remember, I don't forget that it's there, I just forget what its value is, because I know I need to convert this log into the natural logarithm, and I know when I do that I'm going to get the natural logarithm of 2 popping out, but I can never remember if it's underneath or above. For that matter, it doesn't usually matter to me, because what matters in computer science is that it's a constant. It's a constant of some kind. So often, if you'll see me doing this on Scratch somewhere, I'll just write c over n. Some constant over n. Because I know in a second we're doing our big O, little o, and so on, that those constants are about to get swept under the rug. It won't matter what that constant is in a second. It might matter right now, in a second it won't. For the purpose of doing my calculus and doing it correct, on my slide I actually have the actual constant there, 1 over the natural logarithm of 2. And if you want, go double check, make sure I didn't mess this up, make sure it shouldn't be ln of 2 over n. Maybe it is. And I'm not going to double check right now, because I know it's not going to affect the outcome at the end. So if you want to go double check, go ahead. Okay, I'm pretty confident it's right. If it's not, throw it in the comments and give me heck. Okay. What about the bottom? Taking the derivative, well, hopefully, again, this is the simplest thing. This was the first derivative I ever learned, so hopefully we know that derivative. We've calculated that one correctly. Okay. So now what? A little bit of algebra. A little bit of algebra. Well, let's bring that n down. Let's bring that constant down. Okay. So we just sort of joined our fractions together. And now we'll see that that n multiplied into this term here is going to give us an n to the power d. Okay. And now, can we compute the limit? I think so. This is an easier one. And we can hopefully see that constant I was talking about doesn't matter. This is infinity on the bottom. And natural logarithm of 2 times infinity doesn't matter. Okay. So, as I said, infinity on the bottom means yield 0 as our limit, which is the big O relationship that we were looking for. So we're done. Okay. Now, let's think a couple things. What happens if we change the base of the log? Well, let's just change it to e for a second. Then we get natural logarithm of e, which is 1. Does that change the limit at the end? No, remember, because I said that constant out front doesn't matter. So if I change that base to 1,000,000, we just get natural logarithm of 1,000,000. That constant out front still doesn't matter. If we change it to, pick your favorite base. It doesn't even have to be an integer. It doesn't matter. So the base doesn't matter when we're talking about logarithms and polynomials. It's always slower. Okay. Let's think about something else maybe. What if we did log n times log n? Now that one is a little bit trickier, because the calculus gets trickier. But if we, I'm not going to do it because I don't want to go through the extra steps, but you'll be able to see that even log n times log n, you'll need an extra step of L'Hopital's, I believe. But once you have it, you'll again get to the same result. And that's going to show that any logarithm, even logarithms multiplied by other logarithms, are still dominated by polynomials. Okay, this is a rule of thumb that I like to take away. So why do I call it a quick rule of thumb? Someone throws a logarithm on the board, it doesn't matter. Log of 4n squared plus 3n over 2 all squared. And you throw a polynomial up on the board, 4n to the 6 plus 3n minus 2. Which one grows faster? Polynomial every time. You don't even need to think. Okay? Well, you might need to think a little bit. You need to think and remember this theorem and remember this rule of thumb. Logarithms always are dominated by polynomials. Okay, next. Next rule of thumb then. Well, what dominates polynomials then? Well, there's more than one thing that dominates logarithms. There's more than one thing that dominates polynomials. But we're talking about runtime functions here. What's the next likely category of functions that we're going to encounter? And those are exponentials. And I should also be clear that when we're working with these categories, these aren't exactly cut and dry pure categories with firm boundaries. There's something that we call polylogs, which are polynomials multiplied by logarithms, which get weird now. Okay, and you could take polynomials and multiply them by exponentials, and that's a little weird too. So these categories have fuzzy boundaries, but a lot of the times we're working clearly within those boundaries. So, n squared plus 4n plus 2 is very clearly a polynomial. It's not in the gray area. Okay, so here I'm going to pick again two functions. Like I did before, I picked just log n on my left-hand side. So I'm just picking n here. But I could pick any polynomial on the left and this would still be true. Now I picked a very simple one on the left because I wanted to make the right-hand side look, as general as I could. So what I've done here, first of all, I've got an exponential function here, something raised to the power n. What's that something? I picked 1 plus, again, this could be called epsilon, something small, but anything if you want. I picked something small here. Now, first of all, 1 to the power n is always just 1, right? So that doesn't grow at all. That's a constant. That's a simple one, and that's not what we're talking about. But if you increase the base of the polynomial by even just a sliver, like 0.1, 0.000000001, if you like, whatever your smallest sliver is, then it grows. And the maybe surprising thing is that, the function 1.000000001 to the power n grows faster than n. Even though for the first million or however many it is, it's below that cutoff point, that crossover point. But after that point, there will be the crossover point. Let's see if we can prove this particular relationship true as well using the limit test. Okay, so again, using the limit test, pick your a. Let's do our limit. Okay, so now for this one, again, we're still going to get infinite over infinite, so we're still going to reach in our bag and do that L'Hopital's rule. Take the derivative of the top, the derivative of the bottom. So derivative of the top, the simplest derivative, okay. Derivative of the bottom, okay. So this is an exponential function. If it was e to the n, we just get e to the n back again, right? But same thing as we saw before, that if we have not e to the n here, if we have any other base, then we're going to get the natural logarithm of that base popping out in front, okay. Again, that's just from the efforts to convert from this base into base e when we take the derivative. Okay, so in that computation, again, because of the simplicity of the top, we just get the constant. It's now easy to see that since a is a positive number, that this is going to be growing as we go to infinity. It will also go to infinity, so we get 0. And again, that allows us to prove our rule of thumb. Now, what would happen, for this one I just left it as n, but what would happen if I put n squared? Well, after one iteration of L'Hopital's rule, we would get down to n, or 2n technically, right? And then if we were to do it again, we would get down to a constant over, and okay, sorry, the other side of that coin is taking the derivative of the bottom again is just going to pop out another constant, right? So all that's going to change if we change this to n squared instead of n is the constant out front here is going to be different, but as we saw before, as n goes to infinity, that constant doesn't matter. What if we did n cubed? Then we're going to need 3 iterations of L'Hopital's rule. What if we have n to the power of d for some any d? Well, now we just need d repetitions of L'Hopital's rule. I'm going to say that with my hands waving, because that's not exactly correct. That's true if d is an integer, but if d is not an integer, we can still do this, and we can still get to a point where we can show that it is 0, as long as d is positive. Okay, so 2 rules of thumb. Logarithms grow slower than polynomials, no matter the polynomial. Polynomials grow slower than exponentials, no matter the exponential. What's next? Well, there's lots of stuff out there beyond exponentials, but that's like deep outer space. And why do I say that? Well, if we're using this technique to talk about algorithms and how much time or space they're going to use, if you get to the point where your time you're going to be using is an exponential amount of time, you're usually already wasting too much time. You're already too expensive. So if we now go to super exponential, even worse than exponentials, then we just shake our head and say that's never going to work. And so while as a mathematician you might be interested in those functions, as a computer scientist they're really not for anything but argument's sake and for theoretical interest. All right, so I actually do want to sort of end this video with just a comment. We used the limit test as a tool to prove type bounds, but also to prove that some functions dominate other functions, and those are really the main 2 uses of it. And I do just want to remind ourselves of what a type bound means, and then maybe add an extra theorem, which is if f of n is in big O of g of n, and f of n is in big omega of g of n, then f of n is in big theta of g of n. We could prove this with the definitions. And just go look at the definitions and line them up, and it's pretty obvious to see that that's exactly the case. We mentioned that earlier in the last video. Or I say, we can take this as an axiom. That is, to take it as part of the definitions. Maybe take this as the definition of big theta, if you want. That's what it means to take it as an axiom. Remember, an axiom is something we assume is true without asking anyone to prove it is true to us. Just assume it is true in virtue of its trueness. Sometimes we just look at it and say, well, duh, that's true. Like a 1 + 1 = 2 kind of thing. We rarely are going to ask someone to prove that, and if we do, they're just going to say, well, it is. Okay, that's the proof. Okay, so what that's saying is if we have an upper bound and we have a lower bound, and they're the same, they match, then we call this a type bound, a theta bound. And I'm going to leave for the next video the exercise I want to do here, which is, as it says here, can we find and prove some type bounds on these functions, and then place them in order. That is, in order of asymptotic growth rate, and I'm ambiguous here, but I usually mean in increasing order of asymptotic growth rate. So I'll leave that for the next video. So once again, thanks a lot for watching, and we'll see you in that next video.